We are today continuing our use of the internal combustion engine as our fodder for learning how to do things like drawing a component, drawing other components, joining the components together in an assembly, creating motions, and so many things that I think I just like the internal combustion engine because it's a complicated drawing, and it shows you how in any engineering drawing, no matter how complicated, it is made of simple things. No matter how complicated you think an internal combustion engine is, by the time you begin to analyze it, you just see that everything about it is simple. But by the time you continue to add it together, it now looks complicated to the uninitiated. An engineer, the engineer in charge does not see anything complicated about it because he knows that it's a building just made up of the building blocks. So today, we have spent time on the piston. We did several things on the piston. I used the piston to demonstrate parametric design. And we had a few examples and went through a step-by-step process. And today we're going to go to we have been using the connecting rod. We've been looking at the connecting rod. Today we're going to go to the piston. Sometimes I mix these things in a very funny way. We've been looking at the connecting rod. Today we're going to the piston. In the connecting rod, we looked at the parametric design of the connecting rod, as well as just using the GUI. And I'm leaving it to you to use the API to do the same connecting rod. But now, today, it is about the piston. I just continue giving you this motion picture just for you to know that our goal is to be able to do something like this. And we are going to do it step by step. If you look at this, if it looks complicated, it is to the uninitiated. You see that it's just a copy of 6 cylinders with a rotation of firing order. Finish. There's nothing really hard about it. So you did it, you will know it's not hard. But somebody looking at it will think it's really, really complicated. That is how any engineering system might be, because the creator knows what he has done, and he knows that what he did are relatively simple things. We could also have assembled the same engine in a V shape. And even in the V engine, it is still a 4-stroke engine. Each cylinder is 4-stroke. Each cylinder has an intake stroke, a compression stroke, a power stroke, and an exhaust stroke. So that means that you move in a reciprocating way, you move to and fro twice, that is to, fro, to, fro. So that is 4 full strokes. That means that the crankshaft will go through 2 full cycles in the circular motion, which is 720 degrees. And that makes it difficult for you to immediately see that, to see what the firing order is. The firing order is what determines when is what determines the relative position of the fire as you go from cylinder to cylinder. They cannot all fire at the same time. They must fire at different times in such a way that the entire 720 degrees is evened out. So if there are 4 strokes and you have 4, if you have 4 engines and there are 7, the 4 strokes is 720 degrees. If you have 4 engines, so that means that if you divide 720, you divide 720 by 4, that is 180. So each cylinder will be at 180 degrees to each other. One will be at 180 degrees. The first one will be at 180. The first one will be at 0. The next one will be at 180 degrees. The third one will be at 360 degrees. And after that, you have 540 degrees and then 720 degrees. But you will know that the one that is at 0 and the one at 0 and at 360, they would appear to be at the same point. For instance, in this cylinder now, if you look at the right side of this V engine, you can see that cylinder 1 and 4. They seem as if they are at the same point, but they are not. They are oriented at 360 degrees to each other. So that is why you will see that 1 and 4 in the circle I have on the left, 1 and 4 are seeming to be at one point, but it could be that 1 is at 0 and 4 is at 360. Similarly, 2 and 3 look as if they are at the same firing point. They are not. It means that 2 might be at 180 and 3 at 540 or vice versa. So these 4 cylinders are firing all at different times. So this could actually be an arrangement of 1, 3, 4, 2. This could be a 1, 3, 4, 2 firing order, and it could also be a 1, 2, 3, a 1, 2, 4, 3 firing order. So either of those firing orders could be seen visually like this. But the firing order is determined by the time the spark plugs actually gives the fire to each one of them. All this will be synchronized, but that's not our concern here. Our concern is to be able to draw them correctly. So, and then another thing about the V engine is that it has a higher power density. You can see that if you look at this 6-cylinder engine, you can see that the crankshaft is longer. And even though ordinarily this other engine is more powerful, this V engine is more powerful because its own power density is higher. And it's a shorter engine, and it can look smaller, but it is packing a much larger amount of power. So those are some of the things you hear about in the public, but you do not really understand why it works like that. This is the reason. The power density of a V engine is much higher than that of an inline engine. And then I just brought out the inline crankshaft for you to look at. The crankshaft is like this because each cylinder has to be oriented. For instance, if it is 720 degrees, each one will be at 180 degrees to each other, depending on the time of fire. So that is why you have all these orientations. If they are all oriented in the same way, it would not be a possible working engine. It cannot work. It has to be arranged with a specific firing order that will give you a smooth ride. So this is just how one might look like. In this particular one, it could be 154, 156, 423. Because again, in this case, if you have six cylinders and you have 720 degrees, divide 720 by 6. If you divide 720 by 6, you have 120. So cylinder 1 might be at 0, cylinder 5 might be at 120 degrees, and cylinder 6 might be at 240 degrees, and then cylinder 4 will now be at 360 degrees, cylinder 2 at 360 plus 120, and then that's 4, I think that's 480, and so on. So that is how you can achieve a firing order of 156, 423. There are so many other firing orders you can get, but it is the firing order that is going to determine how each cylinder, how each portion of the crankshaft is oriented angularly with respect to the one near it. So that is why the firing order is important here. But again, that is only of use when we are doing the final assembly, but it is important at the final assembly. Without the firing order, you cannot assemble the engine the way we are looking at it. Okay, and I want you to also note that the engines we have been looking at, whether it is a V engine or a 9 engine, were built from a single engine. So a single cylinder. So this is, before you start assembly, you must first of all make sure that you have a properly working single cylinder with all the motions and the displacements and everything done correctly. Once you have that right, you see that the assembly of the full thing is just a piece of cake. So if you do the things right, you just see that this is not as complicated a drawing as it might initially look. It might look forbidding initially, but it isn't if you know what to do. So once we get one right, but how do we get one right? Right now, we've learned how to make the connecting rod very well. Today, I hope by the end of today's class, you will find out the piston itself is very easy to do. So we'll do a piston. And then maybe next week, we'll do the unit of the, next week, we do the unit of the crankshaft and possibly the cylinder and assembly of one single engine. If we do that next week, then next week after that, we will now use the firing order to assemble the engine. And that will be all we will do on the GUI. And then I'm expecting you to now write code to do that with the API. So that is how we're going to go. So 3 weeks. 3 weeks ago, we started with the connecting rod. Past 3 weeks, we have been looking at the connecting rod as a transmissive member, moving, converting reciprocating motion to circular motion. And we use the 3 GUI design, and then we use the parametric design. We have done both. And then during the GUI design, we looked at how we can improve what we had by putting the place for the pin, by slitting the connecting rod into 2 components so that we can remove one part and do an assembly. We've done all of that, and I hope you understood that. So what we're going to do next is the piston. This is an example of a piston we can do, and there is a place here for using the pin to hold the connecting rod. So you put a pin here, the connecting rod is going to be held in this place so that it has enough latitude to move, to make it something like a difficult harmonic motion that will be happening here. So, and then it will be held in place while that is going on, while this is pushing the reciprocating part of the engine, compressing, expanding, and all those kind of things. So this is just a very simple case of a piston. Now, in order to do it, this is, you people kept asking me for the dimensions. Okay, I'm giving you the dimensions that I use here. So this is my own dimension. You can do some literature search and get dimensions that you prefer. It doesn't matter to me, as long as you have a basis to justify the dimensions you are using. So to do this, you first of all take the center point from bottom to a point like 120, like 240 units up on the YZ construction plane. So that's where we are starting. So you do your edge lines of 45 by 50. So if you do your edge line 45 by 50, after that you can constrain them to be horizontal and vertical and give it dimension. Once you do that, you get it in black. And then from there, you can do a horizontal line at 5.5. Let that horizontal line be a construction line and take 2 vertical construction lines. If you take 2 vertical construction lines, everything becomes so simple. So you just join this point to this point with a line, then move here with a line and make it, constrain it to be horizontal, constrain this to be vertical, make this vertical, join it here without dimensioning at first, and just go and complete the circuit. And once the circuit is completed and it's a closed circuit, you will see it will tell you, it will show you a blue color. That blue color shows that you can make a solid with it. That is, you can use that as a profile for an extrusion, for a revolve, for a lofting, for several other things, sweeping, many things you do in 3D. So you will see, if it doesn't show, if it doesn't give you a light blue shade here, that means that there is something wrong with it hasn't closed, and you have to work hard on that. By the time you dimension this 20, 24, 50, this thing want to be 3 and the other want to be 3.5. This is a very simple, shape that you can do in a very short time. And using construction lines is just one way. As you will see later, I did a video here and I did not use construction lines at all. So you may not use construction lines and you'll still be okay. So then after that, you are going to create some lines here to create grooves for the piston rings. In this particular case, I made uneven. There are two of them at 2.5 units, 2.5 units. The third one is 5 units. I saw this in some designs. So in some other designs, they are all equal. So it's if they are all equal, then it is easy to use a pattern replication to do it. But if they are not equal, then pattern replication will not be very good. So that is this. All you are doing here is just to put the grooves in and then remove the connecting line here so that this place opens up, this place opens up, and this place opens up. But you will still see that the rest of the profile is still showing in the light blue, which means that it is still available for the solid body that you can create with any of the tools of creating solids. That will be possible. So this is that can be done that way. And I will just leave you now to hear it. I will play it for you. The way I did it is slightly different from what I just showed you, but let us see.